Hello and welcome to Group 8's project presentation. The title of our project is Numerical Solution and Analysis of the Double Pendulum's Chaotic Motion using Ordinary Differential Equations. At first, I would like to give a brief overview on the whats and whys of the project. So, what is a double pendulum? A double pendulum is basically two pendulums connected end to end. It is infamous for its high sensitivity, chaotic, and unpredictable nonlinear motion. So, here are the problem statements. Traditional concepts and equations cannot easily predict the double pendulum's motion. So, our goal is to make an intuitive double pendulum simulator that gives us the trajectory of the system with precision. Here are the objectives of the project. We are to use MATLAB to simulate a double pendulum simulator, apply RK4 method to precisely solve the ODEs, visualize the chaotic motion and the trajectories using a plotter, and finally implement GUI to make the whole system more intuitive. Now my teammate will explain the theory behind calculating double pendulum's trajectory using RK4 method.
Hello, I am Arnav, student ID 2206159, and I will briefly explain the derivation and implementation of the equations for simulating a double pendulum using the RK4 method. Now, the double pendulum consists of two masses M1 and M2 connected by two rods L1 and L2. And to describe this system, we define the angular positions theta 1 and theta 2 and their time derivatives omega 1 and omega 2 as angular velocities. Then, using basic geometry and physics, we can calculate the kinetic energy and the potential energy of the system and get the Lagrangian L equal to T minus V. Then, we use the Euler-Lagrange equations to get two coupled second order differential equations, but to make them suitable for our RK4 method, we use state variables to rewrite them as four first order differential equations. These are the four equations we are going to solve. Now to solve them, we are using RK4 method, which is basically a numerical technique to solve first order differential equations, and it is famous for its simplicity and accuracy over other methods like the Taylor series method or the Euler's method. Now this method, when given an initial state, can estimate the next value of the function or next state of our system by taking a weighted average of four different slope estimates within a single step. K1, K2, K3 and K4, these are the four slope estimates, and to get the next value of the function, we take a weighted average of these four slopes and add them to our previous value. Okay, now let me show how RK4 method is implemented in our code. Our state vector y contains the four variables theta 1, theta 2, omega 1 and omega 2 and calculate the derivatives using these four equations that we discussed earlier. These values are required to calculate the four slope estimates of RK4 method. Then in RK4 step function, we use these four formulas to determine the values of K1, K2, K3 and K4. Here these derivatives are calculated through the previous function. Then we take a weighted average of K1, K2, K3 and K4 to update the values of our state vector. Then in simulation, we use a loop that calls RK4 step for each time step, and for each iteration, we take the current state, apply RK4 and get the next state and store the result. These stored data are later used to animate the trajectories.
This is Niyaz Morshid, ID 2206158. Our visualize.m function is a sophisticated animation system that takes the raw simulation data from our physics engine and create real-time interactive visualization. First, coordinate transformation. We convert angular position into Cartesian coordinates using trigonometric function. This allows us to plot the pendulum motion in a way that is spontaneous to understand. Second, dual pendulum visualization. We display two pendulums simultaneously with different color. Pendulum 1 appears in solid blue line while pendulum 2 uses red dashed line, making it easy to distinguish between them. The next feature is the trace tracking. You can literally see how two nearly identical pendulum follow completely different path over time. The system integrates harmonious with our GUI, providing real-time control over animation speed, pause or resume functionality, and individual pendulum visibility. We use efficient MATLAB plotting by pre-computing position and updating existing plot object to ensure smooth animation without redrawing everything. The run.m file offers a fast, no GUI demonstration of chaos in a double pendulum system. It sets up to nearly identical pendulum with a teeny different in initial angle. This small change leads to dramatically different motion, visually providing chaos theory perfect for quick demos or teaching. It runs the full simulation and visualization in one step.
This is Abdullah Rohan, student ID 2206150. This is double pendulum GUI code. There is a function double pendulum GUI. This function creates a graphical interface to simulate and visualize two double pendulums with user-defined properties. And there is a visualize function to animate results. Flags are used to control simulation flow during animation. Here we run the code. We can see there are two separate columns labeled pendulum 1 and pendulum 2, where you can input or edit parameters for each pendulum. Theta 1 and theta 2 are initial angles for the two rods of the double pendulum. Omega 1 and omega 2 initial velocities of the rods. Mass 1 and mass 2 are mass of each bob. Length 1 and length 2, length of each pendulum rod. Below this there is a gravity. You can adjust the gravity, and the time shows the total duration for the simulation. And there is a checkbox says level show pendulums. This let you customize the visualization. Show pendulum shows show pendulum 1 displays the trajectory for pendulum 1. Show pendulum displays the trajectory of pendulum 2. Show trace shows the path that end of the pendulum traces over time. This is useful for visually comparing the chaotic divergence of two similar systems. And below the we can the bottom panel there is a start simulation. It begins the animation based on the input parameters, and there is stop simulations, and the function pause temporarily halts the motion. The 2x speed speeds up the animation for quicker observation. There's a right side, there is a plot area. This large white space is the visual simulation area. Once the simulation starts, these pendulums will animate from their initial positions.
This is ID 2206163, and I will now show the double pendulum demonstration. So as you can see, for both of the pendulums, their initial conditions are mostly the same except the theta 2, which has a 0.01 radian difference. So if we start the simulation, we can see that both the pendulums start out on similar pathways, but as time goes on, their pathways diverge a lot. We can hit the 2x speed to speed up the simulation. We can see that by this time their pathways are completely different and totally chaotic. Now we can try some other initial conditions. For example, I will revert it back to 1.57 radians, and for example I can change the length. Let's say we take this 1.2 meter length. If we start the simulation and speed it up, here we can see, like before, that their pathways are completely chaotic and very different from one another. Again, we can set some other initial conditions. For example, I will make this 1 meter again, and Let's say we take the omega. Let's say we take this omega 1.8 and start the simulation. Their trajectories are already very different. So we're going to take one last initial condition test. For example, I can make this vector 2 and let's set the mass to 1.1, for example. Very minute change, but it results in a drastically different pathway. It's also very chaotic and their motions are very different from one another. So what we can gather from these demonstrations is that the trajectory of the double pendulums are very chaotic and intuitively they are very unpredictable. But it is deterministic, meaning that we can determine its position by solving the differential equations related to them, before which calculates their position beforehand. Also, we can see that it is extremely sensitive to initial conditions. Very small changes in initial conditions result in drastically different pathways. So that was it for our project's demonstration. Thank you all for participating.